warahmatullahi wabarakatuh and a very good morning to all our audience. Welcome to Bicara Pakar URL 2022 webinars. This is the fourth series which is brought to you live through Webex, FB Live of Department of Deputy Vice Chancellor Research and Innovation, UTM, and also University Laboratory Management Center, PPMU. You can also catch up our upcoming webinars in our FB page so that you will not be missing out of any updates. Ladies and gentlemen, I'm Noor Shafawani Sarah Saad, Science Officer in UIRL and the moderator for today's session. On behalf of PPMU UTM, I would like to extend a warm welcome and thank you to all of you for joining us today. We really appreciate your precious time. Before that, please mute your line to prevent background noise from disrupting the session. For your information, this webinar is conducted in a series. Starting from the year 2021, this series was successfully organized with thousands of audience who have joined us. We call upon various kinds of field expertise among UTM researchers who have been appointed and collaborated with UIRL. Just to share our latest achievement, I am proud to announce that UIRL has been awarded with ISO 17025 2017 Malaysian Laboratory Accreditation Scheme in 2021. For the years of 2022, we have 4 slots altogether, and the third slot was successfully organized yesterday by Dr. Ernianti. If you missed it yesterday, we will upload the video in our URL YouTube channel. And today's Bicara Pakar URL webinar, we will bring to you another interesting topic to be shared with. Before that, I would like to welcome our honorable speaker, Technologist Dr. Norhayati Mohamed Noor, Research Officer from Institute of Bioproduct Development, IBD UTM. How are you, Doctor?
Alhamdulillah, good. And how are you?
Fine, Alhamdulillah. Thank you, Doctor, for joining us today. I believe the topic that you will share with us will be one of the important sources and knowledge for us to improve our research in the future. So, before I hand over this webinar to our speaker, let me share a short announcement. The webinar will be around 1 hour and 50 minutes and 30 minutes for the Q&A session. Those who have a question, please write it in the chat box or comments in the Webex or FB Live, and I will raise your question to our speaker during the session. Attendance link will be shared in the chat box 30 minutes after the webinar begins for the UTM CPD, and a card points along with the purpose of e-certificate and sharing the video link as well. So please stay tuned until the end of the webinar because we also have some exciting quizzes that you can win, and the question will be given by our speaker along the session. All right, so let me introduce to you our speaker for today. Technologist Dr. Norhayati Mohamed Noor is the research officer who gained her PhD in pharmaceutics from the UCL School of Pharmacy, London, UK in 2017. She gained her Bachelor Engineering in Chemical Engineering in 2004 and Master Engineering in Bioprocess Engineering in 2013 from UTM Malaysia. She has nearly 18 years of experience conducting research and development in cosmeceutical and fragrance area focusing on skin and hair research. She is actively doing research on colloidal system for drug delivery. Her master engineering project was an encapsulation of virgin coconut oil using lipid nanoparticles for improvement of skin hydration and elasticity. Meanwhile, her PhD project was preparation, characterization, and efficiency of lipid-based nanoparticles for topical delivery of hair growth therapeutic molecules. This involved formulation, production, in vitro cytotoxicity, and evaluation of potential for controlled drug delivery to the skin. Currently, she is interested in delivering of hair growth molecules using nanoparticle system through transport follicles region using lipid and cytotoxicity of nanoparticles in the mammalian cell culture. She also have published few chapter original research articles and presented in the local and international conferences in this area. So without further ado, I hand over this webinar to Dr. Norhayati Mohamed with the topic Ask an Expert Particle Size Analyzer. The floor is yours, Doctor.
Yes, Assalamualaikum and a very good morning to everyone. Thank you to our moderator Uh, I'll try to share my slides. Can you see my slide? Sarah, can you see my slide?
Yes, Dr. Can.
Can, okay. All right, so, all right, yes, I can see from my chat box here. So everyone can see my slide. Okay, that's good. Okay, so let's see what we got in to do for today's topic. So I'll try to go. All right. So for today's topic, I'm going to share with all of you today on the particle size analyzer, right? So, but for those who have joined, so for those who have joined our webinar last year, so this is like a refresh for your current knowledge. And for those who are new in this area, so this is quite good for you if you are working with nanoparticles or colloidal formulations that need to use this kind of analyzer, okay, need to use this analyzer to measure your particles. All right, because if you are working with whatever like nanoparticles or micro particles, emulsion and nano emulsions, so this kind of equipment is like a compulsory for you to measure to characterize in term of the size. All right, so even though this is not the only equipment that you can use, you can have another equipment to support your result, right? For today's topic, I'm going to focus only the dynamic light scattering techniques, right? So, and for currently, UPMU has one particle sizer called dynamic light scattering, which is a Melbourne brand. So the model is Melbourne Zeta Sizer Nano ZS. So this is one of the nanoparticles that can use to measure the size of particles. Right. Yes, Miss Sarah has introduced about my background. So a little bit about my, um, I would say, uh, when I involved in this particle size analysis last time, I started use a particle size analyzer since 2008 when I started my master's program. So during that time, during that time we don't have the particle size in I mean in my institute, and so I have to send the sample outside from UTM, which is I send to UPM. So they use this kind of equipment to characterize my formulation. So last time I developed lipid nanoparticles which having a size between 100 to 1000 nanometer for the topical delivery of my virgin coconut oil lipid nanoparticles. And then I continue my PhD in UCL. So during that time, I uh, I think almost every day I spend my formulation and characterization using the particle sizer, which is the same brand the UPMU has currently. So we use the equipments almost every day. So since in the morning 8 a.m. So you can see from right side of my slides. So that is the equipments that the same that UPMU has in the UPMU. So we use at the starting at 8 until someone will stop or switch off at around 11 or 12. It depends on them. But for each of us, we need to just use only 2 hours, not more than that, because we have a schedule, need to book the equipment and use. So normally we will come early in the morning and use that. But most of the us use this kind of equipments. So you can so from the picture, the first one is my professor, which is my first supervisor. I have 3 supervisors for my PhD. So all of us uh, do a research on nanoparticles. So in my group, okay, you can see from my in the middle of the picture, my picture with my other colleagues. So all of us using this particle sizer. So some of my friends use develop a liposome system to deliver a drug. So basically, all of us use drug delivery system, different kind of drug delivery system to characterize in terms of particle size. So they produce like liposomes, they produce like micelle systems, and then they produce like complexations, they produce a polymer nanoparticles. So all of us are working with nanoparticles, but different with other nanomaterials research. Okay, some of them they works on the carbon nanotubes or maybe nano rods. So just a little bit different with our research because we are focusing on the bio or pharmaceuticals area. So the size of targeted applications, it depends on the area of the research. For us, that working with the formulation on the oral or topicals, so basically we just target maybe above 100 nanometer. But some of other research, they really need a very small size of the nano materials, maybe like 10 nanometers or maybe less than 10 nanometers. So this DLS is really good. Okay, it's one of the best equipment that widely used. Even you can find in the published papers, they use quite a lot this kind of model or system or techniques. So this is how I involved in the particle size analysis. Okay, and the best one is if you can see from the below part, which is the right side. So I have attended the conference in US last time. So I met this the inventor of a solid lipid or nanostructured lipid carrier person that invent this kind of research. So I have an opportunity to meet him, and he is quite a good experience for me. Okay, back to our topics for today's. Okay, so today what I'm going to cover for this webinar is a little bit on introduction on DLS. Maybe some of you might be new on this area. So we'll be touch a little bit on DLS, which is a dynamic light scattering. And then the sample preparations, okay, maybe a little bit on the sample preparation for the DLS, because different equipments will have different sample preparations. Okay, for this DLS, they need a certain sample preparations, but not really difficult, not really tedious to perform this experiment, and also maybe the sum of the analyzing the DLS result. All right. All right. So next. So I just because some of the topic that I will be covered today. So if you can see some of the slides might be familiar with all of you. So because we have run the first webinar last year, so the audience have sent a few question and answer to UPMU. So some of them I might be covering for this webinar. All right, some of them they ask what's the difference of the dynamic light scattering and the laser diffractions, because some of them they don't know which equipment is suitable to to measure their samples, because they have develop formulate different kind of formulations, or maybe they have synthesized different kinds of the nanomaterials. So they want to characterize these samples. So which one is the good equipments to measure the size, right? So this is a different of the dynamic light scattering and the laser diffractions. So for the laser diffraction, which is the right sides, so they use the same. I mean, they use the laser that come through this area, and the sample is keep moving. The sample is flowing. Okay, so then the laser will be passed through the samples, and the samples will produce diffractions of the lights. So based on that diffraction, they will calculate uh, using their algorithm in their software. So based on this study, they found that the small um, of particles, okay, you can see here the small of particles will diffract bigger or large diffraction area compared with the bigger size will scattered or diffract the small diffractions. But for the dynamic light scattering, which is on the left sides, it use this just laser, the same. They use the laser, but they calculate the scattered light, which comes from the particles. All right. So meaning that the particle itself in the cuvette is not. I mean the particles is moving because of the Brownian motions. All right. So they just move themselves but randomly, but not by our or external mechanical that move them. Okay, so based on their movement, the random movement, so they have a laser and they will scatter the lights. All right, and then they have a detector which is mostly currently in Melbourne Zeta Sizer. They use the backscatter detector, whereby the detector is just next to the laser around 173 degree. So what happened is if the sample is quite less amount of particles, or the samples is like just a transparent, so the light can just go inside of the cuvette, right? They can go because the light can pass. Okay, but if your sample is too concentrate, you have like a lot of samples, a lot of particles in your samples, so they will the laser just go into the windows or in near to the windows of the cuvette, and the light is scattered back to the detector. So that's the difference between the DLS and laser diffractions, right? So basically, if you are working with nano, okay, when I say nano, it could be maximum to 1000 nanometer, all right? And some of them, they say less than 100 nanometer. So the best option to characterize is using the dynamic light scattering, which is the left side, dynamic light scattering. So because they use randomly movement of the particles. So the particle just move randomly based on their sizes, right? But for the laser diffractions, normally they characterize for the bigger size of particles. For example, you are working with emulsion, okay, or maybe emulsion which having like a sample 10 micron, or maybe 2 micron, or maybe 50 micron. So mostly they use the laser diffraction because they use another principle or another theory, right? Okay, next, we move to the next slide. All right, so when we talk about dynamic light scattering, okay, sometimes they're called as photon correlation spectroscopy. Sometimes they're called as quasi-elastic light scattering. So this is like the same techniques that they use. I mean, the similar name prefer the dynamic light scattering techniques. So this is a non-invasive technique. So means that if the laser pass the sample, is not directly, because we have the cuvette. Okay, the cuvette is just like a barrier. So the sample, the laser just pass through the sample and give effect to the samples, right? So this is a non-invasive, and DLS used a Brownian motions. So Brownian motions is the random movement. So if you have the particle which is small, okay, it normally can just move randomly. Okay, you do not need to give energy to the uh, particles because they can just move randomly, right? So, but they should be in the dispersion of the liquid or maybe the gas, right? The particles in the gas or the particles in the dispersion, right? Then they can move, and then they can um bombard by each other from the solvent of the molecules. So they will move randomly, and then from that measurements, from that movement, they calculate the we call as a size, right? All right, and sometimes they call as a diffusion coefficients, right? So for dynamic light scattering, they measure the speed of the particles. Okay, like I mentioned before, it moves randomly. So it measure the speed of the particles. If the particles is small, okay, you can imagine if the particle is small, they can diffuse rapidly. So they can go up and down randomly and very quick. But if the particle is really large, okay, they will move slowly. So the same thing is like if something which is heavy, they will just move slowly, right? Okay. So from that movement, so they calculate the velocity of the diffusion coefficient of the particles. All right. From these equations, well, they use a Stokes-Einstein equation. So for this equation, it will be automatically calculated using the software. So you don't need to calculate the size. Okay, it will automatically calculate it. Okay, but things that you have to be careful, all right, because whatever that you put your sample in the equipments, they will give you the result. Okay, so if you put the wrong input, they just give you the result, but the result could be not the correct one. So what I can say, this Stokes-Einstein equation is related to the temperature, right? If the temperature is high, all right, so the particle will move very quickly, okay, rapidly. But if the temperature is low, it will move. So that's why when we measure this particles size, we have to add on the informations. So what's the temperature that we use for that machine? Because sometimes they produce a formulation that can release the ingredients or the drugs at certain level or maybe at body temperature. So example, if you have this kind of delivery system that can only release your drugs or your active at that body temperature, okay, maybe around 37s or okay, then it just released. So you have to set the temperature for that machine at 37 or 36. So the temperature also give you significant um, for the particle size. And then the other one also the viscosity of the dispersant. Okay, for dynamic light scattering, the thing is you only can measure the liquid. All right, you cannot measure the solids. If you have the solid, you have to dissolve in a liquid form. All right. So if you have the liquid which is really thick, like sucrose, 10% or 20% of sucrose. So the viscosity is also affect the diameter of the particle size. So that's why when we key in the information into the system, the software, we have to know which kind of dispersant or which kind of solvent that we use to dissolve or to dilute our samples. Okay, this is quite critical. That's why I think for UPMU form, they will ask you, okay, what is the temperature? I think the temperature also included, and also the viscosity, what kind of uh, solution or solvent that you use, for example, if you used ethanol, if you use toluene, if you use oil, which is has a viscosity, it will affect, okay, your particle size results, right? Okay, next. Okay, you can see from here how the particles is moving. All right. So it's not static on one part, but it keeps moving. Okay, even though there is no light, even though there is no movement, so the particles is randomly move. Okay, and they move like no specific area. They can just randomly move. So based on this movement, they try to calculate how far, okay, for this kind of silica particles, okay, over 1 minute, they want to find how far these samples move. Either they move as a diffusion, which is the Brownian, or maybe they move because of the settling, okay, because of the gravity. So it depends. So if you can see from this table, so if the particles is around 1 nanometer, so you can see the diffusion coefficient is quite high, right? It's quite big, it's quite large, because if the particle is small, they can move very rapidly. Okay, compared if the size is bigger, they move slowly, and some of them settle due to the gravity. Right? So this is the calculation that they use to calculate the root mean square displacements. Okay, based on D is the diffusion coefficients. Right. All right. So, what happened to the samples that has laser? All right. So we call as a scattering of light by the particles. So when the particles are less than 1/10 of the wavelength of the lights. All right. So for this machine, particle sizer of the Melvin, zeta sizer nano, ZS. So they use a helium neon of laser 633 nanometer. So if the sample is less than 1/10, so the scattered lights carry the same energy. So elastic scattering. So you can see here, if the sample is really, really small, so the scattering is not angle dependent. So it just scatter like the same scattered patterns. But if they have like bigger sizes, okay, it depends on the angle dependence. So because you can imagine, if you have very tiny of particles and you put a torchlight, okay, so you can see that everything looks the same, so nothing happens. But if you have a light or torchlight, you can need, and then you have a like a bigger size of the, like a ball, for example, like a ball, compared with the ping pong ball and maybe the football. Okay, you can see the scatter is different. All right, so that's why they come out with this scattering theory. So using this small, very small sizes, they use the Rayleigh scattering, and then they use, and for the bigger one, they use the Mie scattering. But everything will be calculated using the equation that they have in the system. All right. Okay. So then when we talk about particle size analysis, so this is one of the things that sometimes it come out into the articles. So sometimes if you are looking for articles, okay, you can see that some of them they mention about the hydrodynamic size. Some of them they mention about particle size. Okay, so it actually is like intercorrelated each other. Okay, hydrodynamic is the hard sphere that diffuses at the same speed as the particle or molecule being measured. So the diameter of the particles diffuse randomly, and you can remember that they use Brownian motions when they use diffuse at the same speed as the particles of them being measured. So if they measured, actually the hydrodynamic diameter is calculated from the velocity of the particles. Okay, if the particle is small, you can see it move random and rapidly. So you can see the size is very small. All right. Okay. Dependent on the ionic strength of medium. Okay, hydrodynamic diameter, or maybe we call as particle size. So it depends on the ionic strength of medium. So the ions in a medium and the total ionic concentration can affect the particle diffusion speed by changing the thickness of the electric double layer. So some of the published paper, there's not suggested to use the deionized water to do dilution, because they said it will uh, uh, give a little bit different results in terms of the size. Okay, and then it allow conductivity medium will produce extended double layer of ions around the particle. All right, so reducing the diffusion speed and resulting in a larger apparent hydrodynamic diameter, because sometimes if they use the DI water, the result might be bigger when you compare with, for example, that transmission electron microscope or scanning electron microscope or FISM. So you can see the sample size is slightly different, okay, because of this ionic strength. Because some of the articles, they suggest to use dilution of 10 millimolar of sodium chloride and NaCl to dilute the samples. But actually, it depends on your sample itself. All right. So if your sample can be diluted with with water, okay, water or soluble, so maybe you can try to check whether how far the difference using the ionic uh, solvents compared with the one which is non ionic solvents. So you can see that different with DI water, which is non-ionic, it gives a bigger size, right? Okay, and then also the hydrodynamic diameter also affect because of the surface structure. So any change to the surface of the particle that affects the diffusion speed will correspondingly change the apparent size of particles. Okay, and absorbed polymer layer project out into the medium will reduce the diffusion speed more than if the polymer is lying flat on the surface. Okay, it depends. So if you have like nanoparticles and then you want it to have something which is coated with the other polymer, so this might be give you different uh, uh, result. All right, because for DLS they measure not the solid of the particle itself, but including the layer outside of the particles. All right, so that's why sometimes you can see that the size is bigger compared with the transmission electron microscope result. So that's why your result is bigger compared with TEM results. Okay, because it measures the total of the particles, including the layer. If there is a surfactants, if there is some other external layer outside of the particles, it can just measure the whole of the particle, including the layer. All right. And also the hydrodynamic size also affect with the shape of the particles. Because if the shape of particle changes in a way that affects the diffusion speed, then the hydrodynamic size will change. Okay, if your sample is not a total sphere, so the movement is different. So it might and will give you different kind of sizes. So for example, like you are doing nano rods, okay, carbon nanotubes. So there is a rod's diameter which movement is not uh, almost similar. So they will give you different diffusion coefficient because they give you different speed, right? Because sometimes you can see that you have like a broad range of samples, right? So might be due of your sizes is not in the sphere form. Okay, so let's see. I have prepared one question for this. So total, I will prepare 5 quizzes. So for this one, we'll see what is the first quiz. So you can write your answer in the chat box. So maybe you IRL team also can check with other, I think from Facebook as well. So my first quiz for today. Okay. So the first one, the size of a particle is calculated from the translational diffusion coefficient by using the what equations? Okay, can you answer? So I can see here Stokes-Einstein equation from Amani SR, and then TS Imai Zaitusheh Dani also replies Stokes-Einstein's. Okay, Yat Yohui Stokes-Einstein equation. Dian Rusti Stokes-Einstein equation. Yes, the correct answer. The fastest one is Amnani SR. So the team can contact Amnani SR for the first quiz. Okay, congratulations to Amnani. So I just give a simple and basic question for you, so that maybe can just give you some refresh knowledge that you already have. Oh, lambat susah je. Okay, maybe you can try for the next one. Okay, I have the second quiz. Okay, for the second quiz. Okay, be prepared. Second one. Okay, what is the other name of dynamic light scattering techniques? So I have mentioned the other 2 techniques before. Maybe you can, maybe you remember what is the other name of the dynamic light scattering techniques? What of? Yeah, Yohui, Melbourne Zeta Sizer, not really correct. Okay, Dian Rusti, answer photon correlation spectroscopy, quasi-electric light scattering. Okay, that's a really long answers. Amnani reply laser, Dr. Yani reply laser diffractions. Okay, I can see the one that correct is Dian Rusti. All right, so photon correlation spectroscopy or quasi-elastic light scattering. So this is the other name of dynamic light scattering techniques. All right, so the correct one is Dian Rusti. So Miss Sarah.
Yes, doctor. I already take the winner. The
All
winner
right,
is
is there any answer from Facebook Live? Because I can't see Facebook. If some people might answer from the Facebook, but
only
from WebEx, yeah.
for FB Live, only for question number 1.
Oh, okay. So now we have the winner.
Yes,
Uh,
already have.
yes, Dian Rusti. So the secretariat will contact Dian Rusti after this. Congratulations to uh Dian Rusti. All right.
Okay,
All
doctor,
right. So
before we proceed to another session, we take a photo for our. We will
all
begin
right.
for our photo session.
Okay. Should I
Uh,
stop sharing?
yes.
All right.
Everybody, please open up your camera.
Stop sharing. All right. Come, switch on your camera.
Yes.
Okay, 1, 2, 3. 1, 3. 1, 2, 3. speech.
Smile.
1, 2, 3. The last one. 1, 2, 3. Okay, done. Thank you.
Okay, thank you. So let me share my slides. So can you all see my slides? And yes, okay. Okay, thank you. Muhammad Asni. All right, thank you so much. So next we move to the next slide. So I have few slides. So always remember that different measurement techniques often give you different sizes for the same samples. Okay, so no one technology is suitable for every job. So each measurement technology has its own advantages and each is often best suited to specific industries or applications. So that's why you as a researcher, you as a student should remember or should find which equipment that you have to use to characterize your samples. All right, because once you select that kind of particle sizer, okay, you have to be constant. All the procedure, all the SOP, all the equipment. So every time we use for this kind of research, be specific, be like if you are working with a nano, which is having a very small size, 10 nanometer, 20 nanometer. So the best is the DLS system. So because one, if you are doing formulation like 100 formulations, okay, DLS is really easy and very quick. All right, you can just, but you need to prepare your sample first. You do some sample preparations, and then you can put your samples in that machine, and they just give you the results. Okay, whatever that you put, they just give you the result. Either the result is good or bad, you as a researcher have to uh, think about it. Okay, is it logic that you have this kind of sizes? So if you have to do some other sample preparation, then you have to proceed with that other preparations, right? So you have to choose the techniques. So which techniques is really suit, and you have the justification why you choose these techniques, right? So for example, like if you're working with a formulation which is having size more than so for your information, for this Zeta Sizer Nano ZP, the limit for the size from that manual is around 8 to 10 micrometer. But if you ask me, okay, I would suggest if more than 1 micron, please use another techniques or another, which is I would suggest laser diffractions, which is very uh, suitable for sample which is bigger size. But if you have less than 1,000 nanometer, so DLS is a really good options, all right, because it just gives you very quick and easy. For the laser diffraction, it's a little bit tedious, okay, because it's not just you put your sample and then leave it. No, you have to do some work while doing the experiment. You have to do some working. So for laser for the DLS, okay, you just prepare your sample in the lab. You pass to the science officer. So the science officer will put your sample in the cuvette and set everything and run the sample. So while the machine is running, so we do not need to do anything. Just leave it to the machine. So it will calculate everything and give you the result. But for the laser diffractions, starting from the first thing, you have to be there. Okay, you have to be there. You have to put your sample because the sample is keep moving. Okay, you have to add on the diluent, the solvents, so that you have a specific reading. Then the machine will run. So it's a little bit tedious compared with the DLS system, right? So that's why if you use this kind of machine, make sure you are using the correct machine, right? So that's my suggestions, right? Because once you select these machines for your research, so you have to do the same thing, right? For the whole of your formulation. You cannot use the first formulation, you use DLS, and second formulation, you use laser diffractions. It will give you the result, but the result might be quite a little bit of error, or maybe not the real error. Actually, it just give you the result, but not really if you want to compare things which is not the same, so you cannot compare them. So you have to be very specific to which kind of particle sizer that you want to choose, and keep use the machine for your another formulations, right? So that's my suggestions. Okay, even the model, okay, of the machine, some of this they use another brand, so some of they use another brand. So in terms of that, sometimes they call the robustness. Okay, they can find the comparisons. They normally they won't give you the correct size of each the sample. It will give you a different a little bit of differentiation of the sizes because they use different maybe they use different laser type of laser, they use different kind of detector, so this will affect the results, right? So next. All right, so this is the one that happened when you have your sample, okay, in the cuvette cells. All right, so the intensity of the samples, okay, will fluctuate based on the Brownian motions. Okay, if you have a sample here, there is a laser that pass into the cuvette that you have the samples you put inside this here. So even you can see here by using DLS, you only need a very small, little amount of the samples. Normally not more than 2 ml. But for safety, just give extra to the science officer because sometimes they need they need to do some because for me, what I did for my analysis, I will put the first one on the cuvette and I will throw the first samples. Just I'm afraid there might be a dust inside the cuvette. All right. So basically, if you have the reusable glass cuvette, okay, make sure that there is no dust because even one tiny of dust or two dust in the cuvette will give you a big difference for your samples. Okay, for working with this one, so normally we have to be very careful, especially if you are working with very narrow and small size of sample, like if you are working with 2 nanometer or maybe 10 nanometer of sample, which is very small. So even if you have one dust, it give you broad of type of your results. So that's why you have to be quite careful by when dealing with the sample analysis. Okay, so for the sample that has a small particle size, so you can see from the intensity of the machines. So you can see it's running. So it will give you quite rapid movement because of the small size move very rapid compared with the large particles. It gives you a very broad of intensity. Okay. Next, okay. First of all, a laser is used to provide a light source to illuminate the sample particles within a cell. So that I mentioned before, the Zetasizer Nano uses a laser with lambda 633 nanometer. So samples that absorb in this region are not suitable for analysis. Okay, for example, if you're working with a fluorescent sample which is having the same or near to this lambda of laser, it might not suitable to use this kind of machine. So might be you have to use another particle analyzer. All right. So most of the laser beam passes straight through the sample, but some is scattered by the particles within the samples. Right. Okay. A detector is used to measure the intensity of a scattered light. As a particle scatters light in all directions, okay, possible to place the detector in any position and it will still detect the scattering. So if you can see here, zeta sizer, they have different kind of models, and each model they have different kind of detector placements. Okay, for the one that in UPMU, okay, they use nano ZS. So most of these as a default, okay, the detector is stated at 133 degree. So what does it mean is if the laser come from here to these samples, okay, there is an attenuator that control the power of the laser that come to the samples, and then it goes to the cell, which is your sample, and your sample will scatter the laser, the lights, and the detector here, which is the A, at 173 of degree. So why they come out with this? Because they found out that by placing this degree enables detection of back scattering and exclude excess scattered light. So this helps to unmask scattered light signal of low intensity originating from smaller particle size. So that's why they come up with this uh, uh, type of placing the detector from the this machine. All right. So you can see here from the intensity, the small particles in the front and the coarse particle at the back. All right. So when they give you this kind of intensity fluctuation, so they convert it into the correlator using the Stokes-Einstein equations, all right? And they give you diffusion coefficients of a graph. So if you can see from the right side of below graph, the small particles will go first based on the time, and the coarse particle will move at the back, all right? Okay, the key parameters of DLS are the Z average size or cumulant overall mean. So sometimes you can see from the result, they mention Z average. So that is a mean of the hydrodynamic diameter. So which is they compile of the whole distribution of the particles, not only one side, okay? And then they give you the PDI, which is the polydispersity index, which is one of the criteria that you have to be quite, I mean, is useful to see how well is your particles behave, how well distribute of your particles. Is it in the narrow size, all your particles in the same size, or your formulation has a different kind of sizes, like in the 10 nanometer, and then another group which is has like 100 nanometer. So PDI will give you more information, and then the width of intensity, the peak of volume, and the peak of number distribution. All right. So okay, then we can see there from the picture of the laser come into the, before the laser come into the sample, there is a attenuator. Okay, attenuator is a equipment that they use to alter the power of laser. All right, the intensity of the scattered light must be within a specific range of the detector. So you cannot have the full power of the laser to pass your samples. Okay, so because there is a the limitation of the detector to detect and to get the result. All right. If too much light is detected, then the detector will become overload. All right. So to overcome this, An attenuator is used to reduce the intensity of the laser and hence reduce the intensity of the scattering. So this attenuator works to alter the power of laser. For example, if the samples do not scatter much light, okay, means that the samples is very low concentrations. Okay, the amount of scattered light must be increased. All right, the attenuator will increase so that it will give more laser to come into the samples. But if the scatter light such for the large particles, or maybe the sample is too concentrated, the amount of scattered light must be decreased. All right, so you can see this attenuator number from your result. I think every time you send a sample for DLS, Miss Atira will give you the result with the graph. If you can see there is a attenuator number. So you can see which number, which is 9 or maybe 6. So that one, it can give you some idea. Either your sample is too concentrated or your sample is less concentrated. So it give you a number. So then you can have a specific idea that, okay, you have to do this dilutions so that the attenuator will give control the power of the laser, right? Okay, and then once the samples get the laser pass through the sample, before that there is an attenuator, right? And then after the samples being attached by the laser, it will give you the correlation function of the sample based on the scattering intensity. All right. So the scattering intensity signal for the detector is passed to a digital signal processing board called correlator. So this correlator will try to have all of your results based on intensity and correlate to give you some of idea of the graph. All right. So this one you can see while you perform the experiments. So it can give you the live what happened to your samples. All right. So the speed of particles that are being moved by Brownian motion is related to the size of particles. So large particle move slowly, while small particle move quickly. So that's why when you have small particles, the graph will give you in the front. But if the sample is large, so it gives you at the back. All right. So after the correlation function has been measured, this information can be used to calculate the size of distributions. So that's why after finish, they will calculate the size distribution. How well is your samples, right? So I think I just move another one. Okay. Okay, so I think I have covered this one also. The purpose of particle size to obtain the quantitative data. So means that you only can get the number. Okay, the number of your size, which is come from that software. So everything come from that machines. Okay, but you cannot see, you cannot look at your samples of the size. So that's why you have what I suggest, you will have to add another equipments maybe to quantify or to validate your results. So sometimes if you use DLS, so you add on with TEM, okay, to see is it really correct, the sample size is similar with DLS or not. So that is another equipment that they use to quantify, to see the morphology of the sample really, because sometimes the samples is come together. So from DLS, you see that your particles is really big. But then when you do the morphology, which is using TEM, all right, you can see that your particles start having the small size. So this is come, maybe your particles start to be because not stable. So it comes to that questions, all right. That's why they come out with the other equipment to validate the samples size. Okay. Okay, I just move. Okay, so then I'll talk a little bit on for how we define the particle size. So you know that in our research, a lot of researchers do a lot of materials. They do a lot of formulations. So some of them is not in the sphere, right? But for DLS system, they as a theory, so they look at it as a sphere. So means that particles cannot be fully described by a single dimension. So that's why they come with radius and diameter based on the sphere theory. So if you have like this kind of material which is not sphere, but it could give you different kind of results because the sample is moving, so the scattered is different, it's not really same positions, so they'll give you different kind of result. Sometimes they give you a size a little bit bigger, some they give you small. So that's why you have to reconfirm with another equipment, which is like I mentioned, the electron microscopes, okay, to see the things. Okay, just a little bit of the advantages of the DLS that I mentioned before is quick and easy. Okay, it's precise operation for monomodal suspensions. Okay, you can see how well distribute of your sample. Is it in the monodisperse, which is the same group of size, or you have a mixture of the particles. Okay, but the limitation of DLS include the it should follow the Brownian motions. All right, if your sample is not following the Brownian motions, or if your sample is really big, so it doesn't follow Brownian motion, then they give you the wrong result. All right. Okay, this one also one of the other question that always people ask. So which one should I report in my articles, in my manuscript? Should I use intensity? Should I use volume? Or should I use a number? Okay, so you have to keep in mind that this DLS system using scattering techniques. So when they use the scattering techniques, they use the Brownian motions of the how well the particles moves. So based on that movement, they come up with the intensity. So the first thing is intensity. Okay, that normally people will suggest you to get this to report your result in the intensity. Okay, that is the best one. But sometimes if you want to see how distribute of your sample, the volume and the number will give you some informations, right? So you can see that, okay, your formulation is not well distributed. You have two kinds of peaks. One is really large, okay, one is small. So then you can get some idea, okay, maybe you have to do something on your formulations, on your size of particles. But the thing is, measuring intensity of lights is the best one. So you have to report the intensity of light for the dynamic light scattering. So you want to report your result. So intensity result is the first options. Then you can see another parameter, which is volume and number, as just supporting your informations, right? Because normally for a researcher, they really want to give a really good result in their manuscript, right? So sometimes if this happens, if they have to know that, okay, if they give you this kind of results, but at the same time your volume and number give you different results, so you have to keep that, okay, maybe your formulation is not really stable yet, so you have to optimize again. So this give you some indicators. All right. Okay, then is polydispersity index. All right. So polydispersity index, the how well distributed of your samples, to measure the heterogeneity of the samples. they call as polydispersity index. So based on the ISO, they found out that PI value less than 0.05 are common to monodispersed samples. Okay, and then while the sample is PDI bigger than 0.7, give you a broad size. Okay, this give you some idea that how well is your samples. Okay, and PDI lower than 0.3 could be like a reasonable or acceptable result if you want to formulate a drug or formulate nanoparticles. Okay, so I just give you some idea here. So this is the instrument that is running. So you can see from the machines. So this is a correlation function that I mentioned before. So you can see here the correlation functions keep moving because this is still running. So the laser comes to the sample, it scattered the light and give you the live result. So you can see that this correlation function is moving. So normally if this graph comes to the front, so you can just feel that, okay, your sample is having a small size. But if your samples is giving you this, the first upper graph give you broad graph, so you can get the indicator that your sample has a bigger or large particles. So this is what happen if you run your samples, right? So this is some of the other result that okay, come to the result that you will have, you will receive when you send your samples. So this is what you can see here. So we want, so it actually depends on your research. So for myself, if I want to formulate a result, if I want to formulate formulations, I want it in the same group of sizes. So it should be one peak, right? But some of them, they want to have two groups of peaks. So maybe they have two kind of co-encapsulation of materials. So it might give you the two peaks. So if they feel that that is your the best in terms of the PDI, in terms of the sizes, then they can report that results. Okay, for example, this one. So they give you a PDI 0.175. Okay, and then give you the size is 563. Okay, another this one. Size which is 167 and PDI is 0.146. So so if you can have a sample with narrow PDI, is really good for you to confirm that your size is really in the one populations, right? Okay, the same thing this one. So if you are doing optimization, you might see this result which you have a different type of peaks. Okay, sometimes you get two peaks, sometimes you get more than two peaks, and they give you the indicator that okay, like this one, the right one, you give you the refer to quality report. So this one, they will mention in that tab, either your result is good. So if your result is good, they say that, okay, the result is meets the quality data. But if the result is not good, probably your sample is too large, your sample is too polydispersed. If your sample is fluorescence, so they will give you some information that from that tab. So you know that, okay, maybe your sample is too not stable, so you have to improve your surfactants. So they will give you some indicator. So from that result, you can see that the potential scenario. So if the Z average smaller than the peak size, so if there is an additional peak at small size due to additive or buffer or components, because sometimes if we add, we do dilutions, so it might be give you the solvent peak, okay, because of the average size lower than the expected peak size. All right. So if the Z average the same as the peak size, ideally is monodisperse sample. All right. So you can see from here. So this is the average. Okay, and then there is the peak size. So they will give you different result, a little bit, not really large, but a little bit different. But if your Z average larger than the peak size, the distribution shows a small and large component. The average of the two is somewhere in between. Okay, under peculiar circumstances, there may be actually not be a smaller or large peak when the small peak is smaller than the lowest display cutoff. So it could be some other materials that involved in your preparations, right? Okay, we come out with the third quiz. Okay, are you guys ready for the third quiz? All right, so let's see. The next quiz is just simple. Okay, blank is the diameter of the hard sphere that diffuses at the same speed as the particles or molecules being measured. Okay, what is that? Okay, I can see from the chat box. Amnani SR. Okay, she answered hydrodynamic size. So what else? Okay, Yat Yohui reply hydrodynamic diameter. Cyrus also answered as a hydrodynamic diameter. Yes, the correct answer is hydrodynamic size. Okay, hydrodynamic diameter. Okay, hydrodynamic diameter is the diameter of the hard sphere that diffuses at the same speed as the particle or molecules being measured. So you remember before when I mentioned that because of the movement of the particles, okay, so it diffuse in that diluent, the solvents, the same speed of the particle. So the correct answer is hydrodynamic size. So normally, if you find in the articles, if you're working with nanoparticles like liposome or solid lipid nanoparticles, nanostructured lipid carrier, sometimes they use a hydrodynamic diameter term, okay, for the particle size. All right. So congratulations to Amnani. All right.
Dr.
Okay,
Amnani
next.
already won the first question.
Oh, really? Amnani won.
Yes.
So sorry, Amnani. So we give to the second one to Yat Yohui.
Yes.
Okay? Yeah. So the committee will contact Yat Yohui. Congratulations. And Amnani, you won the first one. Okay, congratulations as well. So Yat Yohui, you won for this quiz. All right. Okay, the second one, the fourth quiz. I think we move to the second quiz. Okay, the committee has replied. The winner for quiz 3, Yat Yohui. Okay, fourth quiz. So, okay, what is a measure of the heterogeneity of the sample based on size? So this is really quick. Oh wow, that's really fast. TS Irmai Zatushedani, PDI. Okay, the rest. Is there any answer? What is the measure of the heterogeneity of the sample based on size? Right. So what is that? The things that you feel it is quite important in your research. When you see this number, it gives you indicator your sample is homogeneous or not homogeneous. So Cyrus also you reply PDI. Okay, the winner is TS Irmai Zatus Shedani. And Miss Sarah? Okay.
Okay, Doctor. Okay.
All right. So winner, congratulations, TS Irmai Zatus Shahdani. Okay, you have answered that last time as well, right? Okay, congratulations. All right. Okay, this is a little bit on the sample preparations. Okay, maybe some of you might want to know how to prepare a sample. Actually, there is no specific okay, you have to dilute this one into this one. No specific SOP or methods. Okay, it depends on your sample, right? So for the liquid sample, but remember DLS only measure the sample which is in the liquid form. Okay, if your sample in the powder, So you have to dilute. But remember that what is your what is your final products? If your final product really in the powder form, okay, you might not need the DLS, okay, because DLS doing on the liquid form. Okay, so if your sample is really should be in the powder, might be you have to use another techniques, which is maybe the laser diffraction technique, which can measure the powder and the liquid as well. All right, so you have to do some research a little bit. What is your finish application of your formulation? So if your formulation is really in the liquid, then you can dissolve in the sample of diluents. Okay, and then you can measure the size. Okay, for the liquid samples, it depends. Some maybe need to be diluted or some not. It depends on the sample. But it is ideal to dilute the sample in the same exact liquid that was originally prepared. Okay, if your formulation is prepared using the normal distilled water, so then when you dilute the sample, use the same distilled water. But some they use another additives like salts, surfactants, right? So in highly concentrated liquid samples, the samples may appear opaque or milky white. So if the sample is highly concentrated, so let's say if you have very opaque color like fresh milk, right? So then it should be diluted a little bit, okay? So that the laser can go to the sample and scatter the particles. What happens is if it is too much or too concentrate, your samples or your particle it just uh, move slowly, and then it could give you multiple scattering, which might give you the wrong result. You still can get the result, but it give you the wrong result, right? So as a guide, aim to be able to see through part some sample visible. Okay, if you are working with the really opaque like emulsions, right, or nano emulsions, might be you have to do some little bit dilution so that you can see not really transparent like a clear water, no, but maybe some a little bit of samples. It can be like can see through the samples, okay. But some researcher use 10 millimolar sodium chloride solution rather than the pure water. But it depends on the sample. If you are working with micelles, okay, for the micelles, even though it is really transparent, you just see that it's just like transparent samples, clear, but if you do dilutions, be careful that not to break the micelle, because micelle has a certain uh, point, critical concentration point, that if you do more dilutions, so the micelle just disperse and you cannot get the result, or maybe you get a very small size of the particles. In terms of the sample dilution, also need to be very careful. Okay. Okay, this is some of other factors that influence of the DLS results. What I mentioned before, the sample preparations. Okay, for example, if your sample need to be diluted, okay, and then you have to do like a toluenes or DMSO. So make sure that this one also be mentioned in the form, so that the science officer will key in, because they have different viscosity that might affect your results, right? And then any precipitations confirms the presence of bigger particles. Okay, sometimes if you do formulation, you can see with your naked eye there is a big lumps. So you can just imagine that you are not going to have a good size of particles. All right. Sometimes the particles might be having a creaming effect, like floating. Okay, some might be sedimenting. Okay, so you have to be very careful. Okay, like I mentioned before, using the eye water is usually not recommended as an absence of ions that fail to shield the long distance interaction between particles. So that's why you can see that the size might be bigger, larger the actual size compared with the TEM results. Okay, And then sample concentrations. So like I mentioned, so higher concentration might produce a multiple scattering, all right, can give you the wrong results, okay? And then as a result, the obtained size is artificially smaller and unpredictable agglomeration happens. Okay, and two dilute samples may not generate enough scattered light to analyze. So it's difficult to provide a general guideline on the ideal concentration for DLS, and it is varies depending on your samples, all right? So, and then if your sample is colored or fluorescence, okay, in case of absorption, the intensity of scattered light will be lower and hence artificial smaller size for the particles will be estimated. So as a result, in case of fluorescence, there can be heightened noise which deteriorates signal to noise ratio, resulting in low quality data and broadening of peak. Sometimes you can see this notification or maybe your result saying that, okay, refer quality report. So in that report, they might say that your sample is fluorescence, all right? So might be you have to use another methods to measure your particle size, all right? And the effect of agglomeration is difficult to obtain high quality of data from dispersion with agglomerated nanoparticles, as the bigger agglomerated lumps scatter too much light, which may damage the detector. Because for uh, nano synthesizer SP, I think is quite safe because they have the attenuator that control the laser comes into the system, all right, so that it can have a safety. All right, so this is another things that I want to give you information about the things that viscosity of the diluent, your sample that you do dilutions, right? Some they use sucrose, water, methanol, toluene. So they have the different viscosity. So with the same samples, formulations, you do different kind of dilutions with different diluents. You can see the size is different. Okay, by using the 40% sucrose, you have like a 15 nanometer only size. But if you use toluene, give you 153. So you can see that it's quite big, a broader size. If you give the wrong information to the, I mean, when you send your samples, you didn't mention this in your paper, in your form. So they give you the quite, you still get the results, right? You still get the result, but your result is not correct, right? Okay. So the next, I think the last quiz for today's. For today, okay, the next quiz, are you ready? Okay. So for the last quiz for today is, so placing detectors at which degree enables detection of backscattering and excludes excess scattered light. So this is used in the Zetasizer Nano SP. So this helps to unmask scattered light signals of low intensity originating from smaller size. So, okay, I can see the answer. Yat Yohwei reply 173. TS Irmai, Zatus, 173. Cyrus, Norazlan bin Sharbini, 163. Izni Maria, 163. Okay, none of them reply 90 or none of them reply 180. All right, so the correct answer is 163. Okay, but I think Yat Yohwei has won before, right? Miss Sarah?
Yes, yes, already won.
Okay, so and then TS Irmai already won. What about
One.
Cyrus?
No. Cyrus.
Okay, Cyrus, congratulations to Cyrus. Thank you to Yatyo and TS Irma for your trying, for your trial. And then, okay, yes. Thank you so much to all. Okay, I think next is, all right. So I think that's all from myself on the particle size analyzer. So especially on the Melbourne Zetasizer actually. So if you want to know more about this analysis Okay, you can contact UPMU, and then you can contact IBD as well, because now currently IBD and UPMU has sharing facilities for certain equipments. So if you maybe UPMU has lots of samples for this, and might be can pass to IBD to run the analysis. But for the for IBD, we have only the size measurement, not zeta size, not the zeta potential. But for UPMU has size and zeta potential as well, and also the titrations, the which is we don't have in IBD. So I think that's all from myself. Okay, thank you. So maybe we can go to question and answer.
Okay, thank you, Dr. Norhayati, for the presentation and knowledge shared to us. I believe we do have some questions in the comment section from our audience. Okay, question number one is from Akmal Rosa from FB Live. How many grams of sample powder needed for analysis?
Okay, like I mentioned before, okay, thank you to the question. Okay, like I mentioned before, for this DLS, only measure the sample, which is the liquid samples. Okay, if your samples in the powder, so you have to do dilutions, but then still you have to keep in your mind, okay, your analysis, what is your finished products. So it's really in the liquid, so maybe your sample might be need to dissolve in other application, then you can try to dilute the samples. But what I mentioned, try to dilute the samples uh, until you can see that's not to really concentrated. Okay, if you can imagine that you can put some of particles, some of the powder into the liquid, and then some of the shake. Okay, but not really much, because it depends on your sample. If you're making like a protein samples, you cannot shake hardly. So if your sample is if you are doing like a polymer, so might be you have to do some a little bit of sonications, a little bit, but not really much. But some of them, they said, need to stir for 24 hours. So it depends on your sample itself. If they need some preparation of your sample before sending to Miss Atira. All right, so it depends. So do some try and error, dilute your sample in the certain type of diluents, which diluent that you're going to use at the end of your products. Then you can see if it is not really concentrate, but not really less powder, right?
Okay, another question from Zubaida. Assalamualaikum, Doctor. How do we explain the
Waalaikumsalam.
difference of measurement value of specific surface area measured by the master sizer compared to surface area and pore analyzer?
Surface area and pore analyzer. Okay, for laser you mean the master sizer, the laser diffractions, right? Because I think UPMU has another equipment, the laser diffraction, right? Master sizer 3000, if I'm not mistaken. So they use different techniques. Okay, they use the one that I mentioned before in my slides. Okay, they use laser that be diffract from the particles. From that diffraction patterns, they calculate based on the another equation, not the Stokes-Einstein equation. They use another equations to give you the results, right? So that is different. So if you have this kind of samples, because sometimes if you do if you send these samples to two types of particle analyzer, one is laser diffraction, one is DLS, you might get the different result. But if your sample is really in mono dispersed, the same population with, let's say, 100 nanometer in DLS, stable, but if you run for laser diffraction, you might get the same, almost similar, almost nearly near to each other. Okay, but if your sample is not stable, because laser diffraction can detect the bigger size, maybe in the 20 microns, 70 microns. So then give you a different range of particles size, right?
Okay.
Thank you.
Another question from Zubaida. Which one actually accurate and suitable to be used to measure the surface area?
Surface area. So for this one, I think not for DLS, because DLS is measure the hydrodynamic diameter, but probably from that hydrodynamic diameter you can get some idea on the surface area. Okay, maybe you can use another equipment to calculate the surface area.
Okay. Another question from Rosalina Amran. If it
Okay.
can be dilute, so is it not suitable for this test?
Okay, Rosalina. Okay, if it can't be dilute, so it is not suitable for this test. So it depends. Okay, your finished applications. So because some of them they cannot be diluted in water, but it can be diluted into other diluent. For example, like methanol, maybe toluene. So then it can be dilute and can test using DLS. But you have to mention that you are using this kind of diluents so that Atira aware that the viscosity is different, and at the same time the cuvette that they use, is it compatible with that diluents. So if the diluent is like ethanol, ethanol could be okay, but maybe the acetone or maybe something which is harsh chemical that might affect the cuvette, because normally I think UPMU use the plastic disposable cuvette. Okay, that's cuvette has a limitations. If the sample is just use water, there's no problem. But if you use a different kind of diluents, the solvent that you use for dilutions, you have to mention so that maybe Atika aware that the sample can be measured or not.
Okay. Um,
Okay.
okay.
Is there
Another
any
question.
question?
How do I interpret more than one peak in a zeta potential run? Does the surface have more than one charge?
Okay, that one is other topics, which is the zeta potential topics. So for today's, I just cover the uh, particle size. But actually, they use the almost the similar techniques. They use the laser as well to calculate the zeta potential. Okay, but what happened is for DLS, they use the photon correlations or dynamic light scattering. But for this zeta potential, they use electromobility. So which they use the currents, electric, that give current different because that's why for zeta potential there is positive and negative electrodes. So when the current into the samples, so the sample move not because of Brownian motion, but it moved because of the different or changes of the charge of the current. So that's why they will move to the other side and they will move to the other side until they give you some peak, and you can get okay the zeta potential is this kind of amounts. But it also relates with the size as well, because if the sample is small, it can give or it can move faster, might be give you higher zeta potential value. But if your sample is big, okay, it slow and give you low of the results. But that one is under zeta potential measurements.
Okay, maybe this is the last
Okay.
question. What are the common issue present while analysis and how to overcome?
What is the common
Common
analysis? What
issue.
common issue is normally is quite. I mean, it's quite difficult to get the first result because you haven't done the formulation yet. Okay, you didn't know that what is the range of your size, So you might need to do another sample preparation, because maybe the first time you prepare the samples with the wrong diluents, or maybe you can do some optimization of the sample itself. So then it come out with the, because whatever sample that you put in the system, they just give you the results, because there is a software, there is a, uh, what we call as a cuvette that you put a sample and we switch on, then they give you the result. It is our job to analyze the result. Is it good or not? So it depends on your research area. So if your research is nearly to one of these, because normally we try to do something which is related to the previous study, or maybe to other articles or other research. So we can get as a what we call as a standard or method. If they say, let's by using these ingredients you will have this kind of size, then you can know, okay, you might produce the wrong, or maybe you produce the correct result. So it depends on your sample. Every sample has different difficulty. Okay, so if you are doing something which is rapidly the same thing every day, so you know that, okay, by using these ingredients, you know that you have this 200 nanometer. Then you run the experiment, you get the result. Then you are really lucky. But then, in terms of the optimization of formulation itself has, difficulty to get a very sharp and narrow of PDI. I think that's two. The things that always happen to those who are working with nano formulations, nanoparticles, for basically for the biopharmaceuticals. Mm.
So that's all for the question today. If you have anything info or and from you, Doctor?
I think that's all from me. Yes, I think this one is correct. Siti Mariam, BET analyzer can measure surface area and pore size. Yes, I think I mentioned last time, right, by one of our speaker, uh, Prof.
Sorry,
Uh,
Prof.
BET under Prof.
Zaitun.
Zaitun. Yes, I think you can try to send your sample for BET, and you has the equipment as well. I
Okay.
think that's all for myself, and sorry for things that not in the what I planned. So that's all from me. Hopefully you gain some experience, or you gain some knowledge. For those who are familiar with these equipments, maybe just a refresh to your knowledge, right? Thank you so much, everyone.
Okay, thank you and congratulations to all the winners. Our host will privately message to the winners. So that's the end of our webinar today. We hope that you can gain some new knowledge so that you can implement them in your study and research. Visit the UTM University Laboratory Management Center, Facebook and our official website for more information about our instrument services. See you again on the next Bicara Pakar URL. Thank you, stay safe and Assalamualaikum.